calculus. Oh, sorry, the line integral. And today we will review this complex line integral. So we have some idea. I assume that you have already, some sort of rough idea on this complex line integral from the previous lecture, though we have almost, covered everything there. But there were some queries as well, which were open last time. So I think those queries will be also resolved now, and it's a more kind of systematic now, because you have the idea, then I can go in a slightly different fashion now. So the complex line integral, with the portion which I have covered very much in the last week, I will go fast, and something new and your attention is needed, I'll go slowly and I'll mention that. So fz be a continuous complex valued function in some domain D, and then the idea was that this integral along this given path in that complex domain is denoted by such a notation: integral over this curve C. The curve C is given there, and fz dz, and C is called the path of integration. That's what we started with, and we have defined that it's similar to what we do there in real integrals, that you break this curve there in the single integral. We have just the x-axis, and there's interval, and that we break into small sections. So here this curve has to be divided into small sectors, small curves, and then this f xi m is the value between the two, between an interval, and then the difference zm minus zm minus 1, which will be just this line segment between the two. And the summation, if you take the limit, this is exactly precisely the integral we are talking about. So this is some, as you can see, this is some sort of this summation of this function with this interval length. And C is a closed curve, then the line integral is denoted by this closed symbol here, this O over this integral sign, and this fz dz. So this means the curve is closed. So this was what we have discussed already. Now coming to the evaluation part, because this is important, that how to evaluate those line integrals. So there are various ways, and in particular 3 different ways we will consider. Yeah.
What does line integral give? What value and what area, sir?
It's not like area or y, it depends on your application. So sometimes you will be summing over the charge density is given. You want to get the total charge along that path. So sometimes mass, you want to compute this. So it depends on the applications, and soon, I think your third semester or so, you will have many. So this is not just one application. Something like area or so, like in this term you can get the length of the curve. But that is not the real application. So there are many applications in terms of, so in electrical engineering you will find, in electronics you will find, and so many things. So that is not just a one kind of applications. Yeah, wherever you are, some density kind of things is given, whether it's a mass density, charge density, and so on, and then you are calculating the along some given path, that how much total density is there, how much total charge is there, that there you will be using those line integral, right? So the evaluation will focus on the evaluation part here. So fz dz, so fz as we write in terms of u plus iv, right? And dz similarly, because z is x plus iy, so you can write dz as dx plus iy. So it is pretty similar now. So we can have again this complex integral to this real integrals with complex and imaginary part. And then if you multiply these two, and then the second portion we write the complex one, and the first one the real one. So you will get these two integrals, one over this curve u dx minus v dy, the second one is v dx plus u dy, just by simple multiplication of this u plus iv to dx plus I dy. So this is the general, I mean, there's nothing specific here, no special techniques so far. where the C we can consider piecewise smooth and the function fz continues on this curve C. The first technique which will be used for this evaluation of such line integral is without parameterize the curve. That is the easiest one. Sometimes if this curve equation is given in terms of the Cartesian coordinate, a simple curve equation like here y is equal to yx is given and range of x is given from a to b. So you have the sum curve is given here and x varies from a to b, and we want to compute that complex line integral over that curve y is equal to yx. In that case, it is very simple. So depending on either x is equal to yx is given or y is equal to xy is given, you can convert as per the convenience either everything into dx or everything into dy, depending on that relation. So for example, if y is equal to yx is given, then this you go with substitute that x, and for y you substitute that yx. That means everything is in x now. In the second term also v x yx, and then dy also it's a y prime dx. So then everything over dx. We will be integrating everything over dx. In the second term, the same thing, v you substitute your x and y, here also substitute x and y in terms of x of course, because that is the relation given, and then y prime will come because this dy we want to get here. So dy is y prime x into dx, right? So that then everything is over dx, and then you have these two real integrals. Compute this and you will get a complex number or the complex value of your line integral, right? So this is the simplest way of thinking or evaluating the line integral. And I think one example we have done indeed in the last week, where we did not write this curve C into parameterized form and then perform the integral, but directly if your curve is given like y is equal to x square, y is equal to x, some line or mx, then directly you substitute those x and y there and then integrate this. There is no problem. Correct. So for simple curves, most of the time that works well. Now the second is that parameterize the curve, which is more common and more useful, because your curve is given like circle or some sort of those curves where parametric form is given, or it can be written easily, because once you have the you have parametric form of the curve, that line integral becomes even easier. So here you have the path C represented by z is equal to zt, where t is somewhere in the range a to b. So this is the parametric equation of the curve, and then as we discussed last time, that you substitute this for z is equal to zt in the integral, and that dz will become the z prime t and then dt, and then you have this single real kind of integral over t, and you integrate this and you will get the value of this integral. Another possibility, but where parameterized form, because you can have in several forms. Either you write in z is equal to zt form, means xt plus iyt, like here. So you may have that those parametric form is given as x is equal to xt, y is equal to yt, and then we have this z. Quite similar to here, but sometimes this real and complex part may not be easier to separate there. Then you don't have to do directly substitute there and z prime t and then go with that. Otherwise, what you do, you again get back to this splitting there, put in your u xt yt and then x prime t, and then you have integral over dt. In the second portion also you put v for xy, you put xt yt, then you have y prime t dt. In the second integral again you do the same thing, substitute your xt yt in u and v, and you integrate over dt. The same thing. I mean, there is no difference either here or here, but I'm just mentioning this, that both ways are good. So we have the two cases now. One, the equation is written in the parameterized form, or it is not. It is written just y is equal to yx form. So in either case, we are converting actually integral to the real integral of one variable, and then we are integrating those like we do in case of real calculus. Just for instance, if
Sir,
you want to, yeah.
sir, z of t should be 1 function, I think.
Z of t should be 1 1
Uh,
means
sir, is strictly increasing or decreasing type.
Z is equal to ZT.
Yes, sir, z of t should be an 1 function. Otherwise, we will have problem for limits if it will give.
You can have these curves also. Yeah. So as t is varying, you are varying with this, and then you have your curve. It can be circle also, a part of the circle, anything. Piecewise smooth. That's the only condition which we discussed on that day. Fine. Let's just go through some examples, and there will be many. So, for example, we want to evaluate this where C is the straight line joining 0, 0 to 1. It's a simple case. So from 0, 0 to 2, 1. And then the approach one will be that I don't want to convert to any parametric form, but just directly in terms of xy, because we know the equation that is x is equal to 2y, and then you have z square, the integrand, right, in terms of x plus y, then you have ux and vy form, and then the dz also dx plus I dy. So here the dx is easy for me because otherwise half will come there. That also you can do, but let's just change dx to 2 dy, and then you have dy, then you have the dy, dz in the form of dy. Then everything is in terms of dy. You substitute your z square here, and then you substitute your dz there and integrate over y, and the limits of y goes from uh, 0 to 1, right? Then the limit of y goes from 0 to 1, and you integrate that, and you will find the value 2 plus 11i by 3. The approach 2 could be that you write first in the parametric form. For instance, here zt is equal to 2t plus it, and t varies from 0 to 1. That is the parametric form of this curve. And then you can do in one go. So the z square, you substitute that z there, and then the dz is 2 times I into dt, and then you can integrate this, and again you will get, of course, 2 plus 11i by 2. So these are the two ways, either directly in terms of xy, or you do if you can write in the parameterized form. In many cases this is easy, so then you go with this form. So in either case, this is a general approach of evaluating integral in this line integral in the complex plane. And then we will go into more details of or some special cases, because this is the general approach we have already mentioned, that you can compute those line integrals. But now we'll go to more specific cases where the integrand is your analytic and so on, those things. For that we need like simple closed curve, which we mentioned yesterday, that this is a simple closed curve. This is not a simple closed curve because it is crossing itself. We have also discussed the simply and multiply connected domain. So simply connected domain is where every simple closed curve can be shrunk to a point without leaving domain. Or another one I have mentioned here, a domain D is called simply connected if every simple closed curve encloses only points of D. So if you make a simple closed curve here, it will enclose the points of D itself. But if you enclose the curve here in this D, you make a closed curve in this D, simple closed curve in D, then it is not enclosing all the points of D itself, but here, which is not the part of D, is also being enclosed by this curve. So it is multiply connected domain. This is simply connected domain. And then we have discussed the Cauchy integral theorem, right? So far we have discussed the two techniques of evaluating the line integral. One, when you can write your curve into parametric form, and the second one when the curve is given in the Cartesian form. In either case, the idea is same, that you substitute there in the integrand, and accordingly the dz should be evaluated, and then it will reduce to a single integral which you evaluate, and that's all. Now the Cauchy integral theorem, yeah. So the Cauchy integral theorem says that if fz is analytic in a simply connected domain, yeah, you have some D here, simply connected domain, then for every simple closed curve, then you take any simple closed curve in this domain D, then the integral, the closed integral over the closed path C, this is your C here, dz is going to be 0. This is the Cauchy integral theorem. So what are the assumptions that we should again make a note here? That fz is analytic in a simply connected domain. So then fz is analytic in this domain D, and then we are taking any closed path C in this domain, and then integrating this fz over that C, over that curve C, and then that integral value is 0. This is the result of the Cauchy integral theorem. Indeed, we have seen the proof also, so I'll just quickly go through because we have discussed on that day, and mainly it was the theorem from the vector calculus, the Green's theorem. So here what we have started with this, so we have taken that integral as usual. We have this complex and the imaginary part here, and then we will make use of the CR equations, that ux is equal to vx and vx is equal to minus uy, that we will make use of it. And the important point here was that this one, the Green's theorem, that once we know that these are continuous, those ux, vx, vy, and those are continuous, then we have, and this continuity follows actually from analyticity of fz itself. Though in this theorem, as I mentioned, that due to Cauchy assumed this additional stuff that fz is continuous, but that is not required. So later on this was removed, and analyticity itself will give you the continuity of this ux, vx, vy, uy. And with that continuity, you apply this Green's theorem, which converts the line integral to the area integral. And once you have this line integral to the area integral, and the CR equation says that this integrand is 0, because here the equality will make that 0. Vx is equal to minus uy will give that 0. Uy is equal to minus vx will give this integral 0, this first part. Similarly, the second part of this our line integral can be set to 0 here, and this integral is 0, this integral is 0, so this integral is 0, and we proved that the integral fz dz is equal to 0 over that any closed curve in that domain D you take, this integral is going to be 0. So is that clear? The Green's Cauchy integral theorem is clear? Yes. All assumptions of it, yeah? The assumptions are clear. It's analytic only, the analytic in a simply connected domain, and then every simple closed curve you take, then this integral is going to be 0, right? This is the Cauchy integral theorem.
So in the previous class, that one more like with analytic, if fz is analytic, and if the if the path C is not closed, then it was given that it depends on the final and initial points and the primitive.
I will come to that point. I will come to that point in a minute. Yeah, I will come to that point. So far we have the two integration techniques when the curve is given in parameterized form, or it is not, it is given in the Cartesian form. You can compute that integral. That is a general one where you don't need this analyticity and this connected domain and so on. A curve, piecewise smooth curve is given, and that fz continuous function is given on that, along that curve, and you can integrate it. Very simple, right? Very simple, but very general. Now here we are going to somehow the special cases. One is this Cauchy integral theorem. That is a line integral, but this Cauchy integral theorem says that such a line integral over this closed path is going to be 0 if fz is analytic in a simply connected domain D. Fine. Cauchy is clear?
Yes, sir.
Okay, now I will move to those cases, and you please pay your attention. So there are few new stuff now. The remark. The first remark says Anyway, these remarks are trivial. The condition fz is analytic is sufficient. The first remark is that the condition that this fz is analytic in D is sufficient. That means there are functions which are not analytic in D, but still that integral may be 0. But if it is analytic, 100% it will be 0 because of the Cauchy theorem. But integral may be 0 for other reasons also. I mean, we don't know. The integral can be 0. I mean, there is no point that we say integral will never be 0. So, but that is not due to the Cauchy integral theorem. So what we are saying here that the condition fz is analytic is sufficient. It's not like necessary that without this it cannot happen. Without this it can happen. So this is a sufficient condition. Why it is sufficient? Because or we will see probably on that day we have seen such integral that one can easily show that 1 over z square dz is equal to 0. This integral is 0. Yeah, you can check yourself. You just take a unit circle around this origin, and then the method which we have discussed before, how to evaluate the line integral. You will realize that the value is 0 of this integral. So this result shows that this is not actually because of the Cauchy. Yeah, because Cauchy you cannot apply. 1 over z square is not analytic in the whole domain, in the whole this center 0 and some radius or unit radius. So this is 1 over z square, z equal to 0. The function is not defined itself, so it is not analytic in the whole domain, right? So this result 0 is not because of the Cauchy. It is just because that integral is 0, but nothing to do with the Cauchy integral theorem. Is that clear? So this fz is analytic in D is sufficient for proving this result that integral fz dz equal to 0. The second remark is that simply connectedness of the domain is essential one. I mean, that is important that the domain is simply connected. There should not be any problem in the domain, because there again we can show, or on that day this example was also considered for the evaluation. 1 over z dz over the curve C, where C is again the unit circle lying in this well. So what is C here? Let me just draw this. It's annulus. So here you have the half radius circle, and then you have the 3/2 radius circle, and our domain is this one. And the C is the unit circle somewhere lying in this, because it's a unit circle, so it will lie somewhere in between, right? So it's a unit circle here. So our domain, if you consider that domain here, it is 1 over fz is analytic, right? This is analytic. There is no problem. C is closed. There is no problem. But the value is not 0. Why it is not 0? What is the reason here?
Because the domain is not simply
Because
connected.
domain is not yes, domain is not simply connected, it is a multiply connected. So the domain, the simply connected domain is the essential one. If you don't have that simply connected domain, you don't expect the result of the Cauchy. Okay, so these two, just that fz is analytic is sufficient, and this is essential. Yeah.
So, but by remark 1, if f of z is analytic in D, then automatically f of z dz should be 0, no? But so, here in remark 1, so but in remark 1,
in D, where D is simply connected domain.
Okay,
Yeah.
so, okay.
Then this is true. That is the result of the Cauchy. Then.
Okay, so.
Now I am coming to the point. Independence of path, a consequence of Cauchy integral theorem. Yeah, independence of path. What is that independence? If fz is analytic in a simply connected domain, then this integral is independent of the path in C, path C in D. That is what first we will show that here. So quickly, please pay attention because we don't have much time. So here, for example, I want to integrate from P to Q. Yeah, over this path C1. Over this path C1. I have also attached this Q to P again by some C2 here, so that I have this closed curve C1 to Q here, and along C2 I'm again to P. It's a closed curve, right? Then I can apply the Cauchy integral theorem if my because there is a domain here where your fz is analytic, so we are not worried about this. Okay. Then here C union this, so this curve, this, and then back to this. Over this, fz dz is 0 because of the Cauchy integral theorem. Is that correct? Just say yes or no quickly. Yeah.
Yes, sir.
Okay, very
Yes,
good.
sir.
Then this one we can break into C1 and C2 star. That is the property of the integral. That
Yes, sir.
this integral plus this integral is equal to 0. Again, the same result, the Cauchy integral theorem. Instead of that C2 going into the direction, I change the direction of the C2 now. So my C1 is also going from P to Q. My C2 is also going from P to Q, some other curve, do different curves C1 and C2. Here the C2 star was going in this direction towards P, so Q to P. Now the C2 has P to Q. So that this one here, the second integral will be minus over C2, right? Because I changed the direction of C2 star. And this result says that integral over C1 is equal to C2. So there was no specific, C1 and C2 were taken to arbitrary C1 and C2. The values are whether you take the over C1 or C2. So this shows that independence of path. Whenever you have a domain which is simply connected and fz is analytic in that domain, then those points P and Q matters, not the curve. Whether you go with this curve, you go with this curve, you go another curve, you go another curve. That curve will not matter. That path will not matter how you are approaching from P to Q. And this is a simple result which is coming from this Cauchy integral theorem. Is that clear?
Yes,
Yes,
sir.
sir.
Yeah, so it is a path independence. Once those assumptions are there that fz is analytic in a simply connected domain, then you take any path, yeah, to reach from P to Q. It's independent. So the value of the integral between 2 points is independent of the path if fz is analytic throughout a simply connected domain containing that path. Well, another one sequence of this independence of path, existence of primitive. What we will see here, that if fz is analytic in a simply connected domain, then f has its primitive in D. That is, there exists fz, so that f prime z is equal to fz. That is another result, and very simple to derive from there. Existence of primitive. If fz is analytic, then there will exist this big F, so that big F prime is equal to fz. Just this sketch of the proof again, I will skip a bit here because it's a lengthy proof otherwise. So consider this Z0 in D. You have some D, fix any Z0 there. And then due to independence of path, we can define the function fz. Z I am varying here. So for example, I take Z here or anywhere. So this is my Z, which is anything, anywhere there. So then for fixed Z0, my integral z0 to z fz dz, what it defines a nice function, right? Z0 to z fz dz, it is a function because it depends on z, nothing else. You have a you have it. It will not depend on any path, that how you are approaching from z to z0. It will not depend on the path. It will depend on what is your z. That's all. You have a different z, value is different. You have a different z, value is different. Nothing else, right? So this z0 to z fz dz is some function of z, and I have added some constant a because a will depend on this z0. So where you are starting actually in this domain, because if you start from here and then go to z, the value will be different. If you start from here, the value will be different. So definitely, I mean, endpoints, it matters with the endpoints. So the upper z, we are anyway taking a variable, but z0 we have fixed some fixed z0 in D. The idea is that we can define a function fz. How our function is defined, the integral of this fz dz, correct? And that we are denoting with big fz. So, and this z, because of the confusion in the limit also we have z, you can replace with some other name. For instance, here I have taken xi. And then the idea to show that this f prime z is equal to fz is a fundamental theorem of integral calculus in complex variable. So the formal proof it is lengthy, which starts with fz plus delta z minus fz over delta z minus fz, where with this integral you can have just z to z plus delta z fz minus fz dz, and then you use the continuity of f and independence of path to approach from z to z plus delta z, just a straight line you can take. And then one can show, so some details are missing, that this is less than epsilon arbitrarily small epsilon. So where you show that this difference between this quotient and this fz can be made arbitrarily small, and then you pass this limit delta z approaches to 0, and this becomes f prime z, and this becomes fz, and because this is arbitrarily small, so that these two becomes equal. And so here some details are missing, but important is, I think, the result that if fz is analytic in a simply connected domain, then f has a primitive fz such that f prime z is equal to fz dz. And the formal proof is there, but directly from here you can realize that because we have the idea already of the fundamental theorem of calculus from real analysis. So if such a relation is there that integral of fz is this big fz, then the derivative of this fz will be just a small fz. So this is the idea that analyticity of fz will give you that primitive of fz, which is big fz, so that big F prime is equal to fz. So if you don't want to follow this, forget it, but just remember that if fz is analytic in a simply connected domain, then it has its primitive. But again, the simply connected domain is important where fz is analytic, then only these results are coming. Another consequence where the fundamental theorem of the complex line integral is coming, so similar to what we have already done actually before. So if fz is analytic in a simply connected domain, then all paths C in D, joining the 2 points z0 to z1, we have this result. See, the primitive thing we have already proved, and that the rest is nothing. So if fz is analytic in a simply connected domain, then instead of doing that integral what we have done before using parametric form and so on, you can directly do that. But again, for that the simply connected domain D is important. It is not just the curve where we will be looking our function, that our function is nice over this curve, so no matter can we do using this primitive technique. But no, if there is any problem anywhere there, then this result will not follow, and you have simple examples which are showing this, like we have seen already this 1 over z dz, which was 2 pi I, because that domain was not simply connected. So the simply analyticity in a simply connected domain is important, then only you can apply this result. So again, if you want to see the sketch of the proof, so since this integral is independent of path, we can define again this function fz, because it will depend only on z. For fixed value of a, it will depend only on z. So for different value of z, you have a different value, and that is just what we are denoting with the big fz, and a depends upon this fixed constant z0. So if we just substitute in this relation z is equal to z0, what is your a? A is nothing but actually fz0, right? A is nothing but fz0, because at z0, when you have z0 there, z0 to z0, that is obviously 0, this integral. So fz0 is, this constant is nothing but fz0. That means we have this relation that fz minus fz0 is equal to this integral, and for any value of z, this is true for any value of z. And if you pick this z is equal to z1, so the result follows here. So fz1 minus fz0 is equal to z0 to z1 and d xi. So this is the fundamental theorem of exactly of complex integral, that if, but here the condition again, right? It is not that fz you will be looking for over the path whatever is there here, because it does not depend indeed on path. It depends, this integral depends only on z0 and z1. And in many cases you know the primitive. So once you know the primitive, you just get the value of this integral fz1 minus fz0 equal to the integral value where you know the primitive. If you don't know, you apply that first technique, put that substitute there and integrate it, there's no problem. But if you know the primitive, which is the case in many cases, then you can apply this fundamental theorem of complex line integral. For example, the same example problem if we take, where we have this straight line, or actually any curve between 0 to 2 1, we are not worried about the straight line. We have done that calculation earlier with the straight line. But if it is any curve, does not matter, so we can do that integral, because that will depend only on 0 and 2 plus pi, and nothing else. We know the primitive also, z cube by 3, then 0 to 2 plus I, and then you substitute there and you will get that value, same value which we got earlier with that parameterized form, or directly by doing this x is equal to 2y form. So because here we can apply that fundamental theorem, z square is analytic everywhere in the entire complex plane. So if you are integrating from over this straight line, we have written a straight line, but does not matter actually what is the curve here joining these 2 points. It can be any curve, does not matter. So the value will be 1 by 3 2 plus 11i. So that is because of that fundamental theorem of integral, complex integral. Another remark which we have, I think, gone through, so I can quickly move here. The Cauchy theorem can be applied to multiply connected domains. So if we have, for instance, this domain here which is multiply connected, and then the result was derived to make a cut here, and then you have a simply connected domain, and then in the simply connected domain we can apply the Cauchy mean value theorem. But then if we expand this one, then we realize that this AH and this HA will cancel out, and then we have this result here that A, B, D, E. So this one here which is anti-clockwise, and the another one here, the internal one, that is a clockwise. So sum of these two is going to be 0. So this is the result here, where you remember that in this particular case C1 is taken as anti-clockwise, C2 is taken as clockwise. And indeed a more general result also we discussed that there can be several cuts there, and the result will follow that integral over the C curve, and all other inside have the opposite direction, then you just add them. And another result which will follow, that if you take the direction of all these curves in the clockwise direction itself, then this will be a kind of equality, that C1 is equal to C2, or C is equal to all these C's there. So which was that remark 3, if you remember, on that day when we have taken the same direction of the curve bounding this domain, and then we realize that nothing but the integral over the C1 is equal to integral over C2. So see, again, kind of path dependency you can see. So the integral over this one, the outer one here, you can take any one, any curve here inside, any curve here inside, the value is going to be the same, right? Or the C2 itself, or any curve you take, the value of the two will be equal there. This is what the meaning of this result. So the summary, if I go in last 2 minutes, what we have learned in previous lecture and also today, that once a line integral you need to evaluate, you can do without parameterizing the curve. So y is equal to yx, substitute there in u and v, u and v, and then evaluate this simple one-dimensional real integrals. If you can parameterize, or it is given already in the parameterized form, it is much easier. You substitute that parameterized form there and z dot and dt, and you are done. If fz is analytic in a simply connected domain, then there are two scenarios. One is if you have a closed curve in C in D, then the value of this integral is equal to 0. The second situation we have dealt with, that there exists an analytical function fz that means that primitive, there exists a primitive, so that f prime z is equal to fz in D along any path z1 to z2. The integral here will depend only on the endpoint. The value will be fz1 minus fz2. So these are the basically the three ways you have to keep in mind. In fact, the first two are more or less the same. So the same technique that you are substituting there, those parametric form or direct the given function. So it's the same thing. And the second, when you have this analyticity in the domain, in a simply connected domain, then either you can apply this one if it is not closed interval, and you can find the primitive of the function in some simple cases, or if you have a closed curve, then you can apply this Cauchy integral theorem, and that value will be 0. So this is what we have learned in so far. Tomorrow we are going. This is going to be the last two lectures. Though we have covered most of the things, most important things, if you understood those line integrals, we have some more generalization of this Cauchy integral theorem to get the derivative of the functions and so on in terms of the integrals. So those we will complete tomorrow, and I'm sure tomorrow we can finish this line integral, and that is the topic of your for your exams. Also, we have not included anything else beyond this line integral in the examination. Yeah, so that is all we have discussed related to integral today. So if you have any